Hi folks, welcome back to 6.1, Area Between Curves, and we are on question number 7. So this question says find the area of the region bounded between the graphs of 2y squared equals x plus 4 and y squared equals x. Now, this is definitely different from the other pictures in the sense that, and it's also different in terms of the equations. I look at the equations and I see a lot more y squares, which I didn't see before. So I don't have it like y equals anything, okay? But let's see if we can match the graphs. So of the graphs, the one that is the purple one is going to be this y squared equals x, because it's just a parabola, but a sideways parabola. That leaves the other option to be 2y squared equals x plus 4 is the green graph. Now we're going to do things a little differently here, okay? I'm still going to shade the region that I'm trying to find the area of, okay? So that's going to be like this part in here, all right? But when we look at all the other examples we've done, we've gone ahead and drawn vertical lines. And so there was sort of a top curve and a bottom curve. And if I drew the vertical line here, I would have the green one on the top and the purple one on the bottom. But if I drew the vertical line here, I would have the purple line on top and the green one on the bottom. And then back to the first one I drew, well, that one is green on the top and green on the bottom. So this doesn't make it very easy for us to find the area if we use dx. All right, so these vertical lines, lines that cross the x-axis, have all been dx. So we're going to sort of change our perspective, and we're going to try using dy. That means instead of vertical lines, we're thinking horizontal lines, like this. And if I look at that one, the right curve is the purple one, and the left curve is the green one. Well, let's check a few more lines to make sure this pattern holds true. This black line has the purple one on the right and the green one on the left. This black line has the purple curve on the right and the green on the left. All right, so if you can find a consistent pattern to which one's on the right and which one's on the left, what you can actually do is use a different version of the area formula. So in this case, we're going to say the area equals the integral from c to d. So we're not using a to b anymore. We're using c to d of the right curve minus the left curve. So instead of top minus bottom, we're doing right minus left. And instead of a dx at the end, since all of those horizontal lines cross the y-axis, we're going to do dy. So this is an alternate version of the formula that can be useful when graphs, especially like this one, kind of look sideways, okay? And our c and d are actually y values. So here is one intersection, and the y value we want to use for a is -2. And our other intersection is here, and so the y value we want to use at the top is 2. All right, so let's fill in our numbers. The integral from -2 to 2 of the right curve, which is y squared, minus the left curve, which is, we actually have to take this 4 and subtract it to the other side. So we'll get 2y squared minus 4 dy. Okay, now let's simplify and integrate. So distribute -2 to 2, y squared minus 2y squared plus 4 dy equals the integral from -2 to 2 of negative y squared plus 4 dy. All right, time to integrate. Negative 1/3 y cubed plus 4y, plug in 2, plug in -2, which equals negative 1/3 times 2 cubed plus 4 times 2, top bound, minus negative 1/3 times -2 cubed plus 4 times -2, bottom bound. All right, let's work this out. We get negative 8/3 plus 8 minus in 8/3 minus 8. And again, I kind of do this in 2 steps so I don't mess up my signs. Negative 8/3 plus 8 minus 8/3 plus 8 is going to give me negative 16/3 plus 16, or let's give everything a denominator of 3. So 3 times 16 should give us 48. And then the numerators combine to make a 32/3. Okay? So the first question where we've taken sort of a different perspective on this, literally a sideways perspective here, where we are drawing horizontal lines because at least then it's consistent. We have right curve minus left curve, okay? Now I'm actually going to do this show you one potential shortcut that you might want to use in situations like this to show us that we could get to the same answer in a slightly different way. And so I'm going to go back to the picture here, and some of you might have noticed right off the bat that this is a symmetric situation, meaning that if I divide right here, then the top half of this shape is the same as the bottom half. And so what I'm going to do is actually use that to my advantage. So in the pink, I'm going to say I'm going to do 2 times the integral from 0 to 2 of negative y squared plus 4 dy. Okay, so basically I took this line and I said, hey, instead of plugging in from -2 to 2, I want to use symmetry. So I'm going to go from 0 to 2 and then double my answer. So let's see how that simplifies our calculations. So I have 2 negative 1/3 y cubed plus 4y, plug in 2, plug in 0, which equals 2 times negative 1/3 times 8 plus 4 times 2 minus 2 times negative 1/3 0 cubed plus 4 times 0. And sorry, that's a 4 times 0. Well, guess what happens to that whole last term? Everything goes to 0. That definitely makes your life way easier. And then you have 2 times negative 8/3 plus 8, which gives you negative 16/3 plus 16, which gives you 32/3. All right, so for those of you who prefer to use symmetry, that's totally fine. Just make sure that you see the symmetry and that it is indeed evenly split. You can't just like assume that it's cut in half. You have to be able to know that it's cut in half. All right, so folks, that is question number 7. Come on back. We got one last example in this practice packet to go over. See you there.